Hey everybody, here is the supplemental video for our assignment 2. This assignment is going to be using recursion, and what we're going to be using is sort of a backtracking method or a backtracking type method to construct this KnightTour problem. So the first paragraph or so, I think the first half of the paragraph is a little bit just me sort of goofing around, but the idea for this program is you're given an 8x8 chessboard and some initial position of the knight, and you want to be able to construct a tour where you want to have each move sort of labeled, so you kind of are able to construct sort of the tour of a knight that sort of will touch every single spot on the chessboard. So let's go ahead and first go over what I mean by this, and then we'll go into the actual details of this problem. So here is our 8x8 chessboard, and let's say for right now we happen to put the knight happens to initially be right over here, just like that. So I guess K for knight. And I guess our indices, I guess I'll label this in the following way. So we'll use this convention. This will be our row indices. This will be, sorry, column indices, my mistake. This is my row indices right there. So knight initially will be at row 5, column 2. So basically, or other words, this will be the first spot. So that the counter right here, so let's say the 1 over here, is going to be the starting spot of the knight. Now there's actually many spots knight can go to. So actually there are 8 total moves for every location knight is currently on. There's a max of 8 total moves. So a knight always moves in some kind of an L-shaped kind of motion. So we go ahead and use different, use purple, I guess. So knight could actually take this path to go to this spot over here. So it would go up 2 spots and over to the right one, or knight could do this. So it'll end up being at this spot over here. The knight could take one sort of, it jumps up 1 and over to the right 2 spaces, or it can go up 1 and to the left 2 spaces. Or a knight could go down 2 spaces and 1 over to the left, 1 down to the right, and then like this, and like this. So basically those are the 8 possible moves knight could make. So it sort of either moves up. So if it moves up 2 spots up, then it can go to the left 1 or to the right 1. If it moves up 1, it can go to the right 2 and to the left 2. And the same idea other direction. Those are 8 different possible paths. So you want to construct a tour basically, so you have every single spot on this board filled out. So for example, what could happen is you could have something like this. This is maybe not the final tour, but you could have it where knight could end up choosing this spot over here. So this would be the second. So we start off at this position right here, and the second spot would go over here where this 2 is, and then from here the knight could maybe go over here, let's say. That'd be move number 3. So we're simply counting the move. So it first started off here, then it went over here, then it went here, and so forth. And we want to sort of construct a tour where every single spot on this board has been filled out is our goal. So basically pretty simple to determine all the legal moves of a knight. The only hard part now is constructing all this tour and filling this entire board out. So let's go over the class sort of the class content and go over that next, and then sort of keep resuming this problem. Okay, so basically this is going to be our class we're going to write. So I wonder if I can zoom out a little bit here. Okay, so you can put it all into one. Or almost all of it is going to be here. So anyway, so we're going to have this struct position defined within our class knight type. I'll go over this in just a little bit. I'm going to first go over the simpler content before I go into the more complicated content here. So anyway, we have our initial sort of default, or kind of our default constructor. So we'll accept an argument, but this constructor has a default argument, which really means that if you don't pass anything into this constructor, then 8 is going to be passed to that parameter. So let me go down here to the definition. So we have this constructor here, int and then dim for dimension. If I don't pass anything into this constructor, then dim will automatically have the value 8, which I guess we're going to be using 8 by 8 anyway, but I guess this makes it a bit more generic if you didn't want to have a larger board for some reason. So then let's go over our private members next. So let me see here. Okay, so we have this vector right here, board. That's going to simply be a two-dimensional array, two-dimensional vector of integers. So going back to the OneNote for a second, let me see if I can get this to show up. All right. This will be our board basically. We can see here it's a two-dimensional array of integers. So that board is going to have the numbers or the tour index, so the move index for the knight. So let's say, for example, you could have 1, 2, and 3, and the rest of the board will be filled up with numbers basically. That's going to be stored in our board object. That's that. So then we have several other functions. I'll go over the more simpler ones. So we have this Boolean fullBoard, where this function returns true if the entire board is filled up. So basically in this constructor, what we do is when we have this 8 being passed in, we're going to allocate an 8 by 8 vector and assign all zeros to every spot. So the fullBoard function is going to be called in some of these functions here, which we'll go over in a little bit. fullBoard is going to return true if every element on our board contains some number that's not 0. That means we completed this KnightTour. It returns false if there is at least 1 0 somewhere on our board. Pretty simple. And then we have our output tour function. This simply just outputs our complete two-dimensional array and also outputs this functions called counter, which I'll go over how we're going to use this as well. So basically in our output, I guess I use letters instead of numbers, I guess, for the output, but basically this is going to be the whole output board function. It's actually this and this part there. It tells how many functions were called and outputs the entire tour. So for our first sort of input, we start off over here for a knight, and then knight shows this spot. Then from here we chose this spot, then we chose this spot here, and 5 is over here, and so forth. So the entire board is filled up. So we're going to go ahead and write that code to do this. So now is going to come the more complicated contents. So we're going to go over obviously the recursive function. This will use recursion to write this program, and of course what this position sort of struct is all about. All right, so the position struct is going to mainly be used when trying to pick our next position when our knight is currently on some position on our board or on a certain location on our board. So a position has a row and column index, and it has the amount of onward moves possible from that new position. This is a little bit confusing in a sense, but I guess if I explain it here, it might help you sort of see how this can make the process of picking the next position a little bit easier using this struct position. So basically this function is going to sort of be used in a sense. I'm going to go over this function right here and how it correlates with this struct position defined over here. So let's go ahead and go over how does a function getAvailableMoves actually work. So let me go ahead and bring up the OneNote once again. So let's suppose we are currently at this position right now. So we're currently at row 4, column 5, right here. So from this spot, well, we have several possible moves you can make from here. So there's at most 8. So if you look at this, well, we could go over here to this spot. This is a possibility. Or we could go over here. We could go here. Well, we can't go to this location there because we already have a number there, so we're not going to actually choose this one. So we're not going to regard that. We're going to sort of discard this location. We could go over here. We could go over here. We could go here. This is actually 7 moves you can possibly make. There's 7 legal moves you can have because, first of all, the possible move has to be on the board first and foremost, and that location cannot have a number. So right now, at this early stage of this run of this KnightTour, these are 7 possible moves you can make. Okay, so each of these, we're gonna basically in that function. I'm gonna go back to the PDF. Let me summon the PDF. So in this function, getAvailableMoves, in the function right here, you're going to pass in the current index a knight is on, essentially. And what this function will do is returns a vector of position objects, telling us all the possible moves it can make. So in this particular, if we were to call this function getAvailableMoves from this situation that we have right here, it will return a vector of size 7. For 7 position structs. And each of these, we have to store the row and column into each of these objects. So we're going to basically, in this function body, we're going to create a vector object of type position, and we're going to do a pushback, insert a position object onto it, and update the RNCs accordingly. Oops, it's not what I wanted to do. Update the RNCs, and then what we want to do is we have to store how many onward moves from that location we can make. Let's first go over, let's just maybe for right now go over this object over here. Okay, so for this one, I guess I'll use maybe, I guess I'll use green. So here, R would be 2, and C would be 6. And I guess I'm going to just put this over here on the side. O, so the onward moves we could make from here. I think actually these is rows, columns, and onward moves, I believe, in this story. Let me just double check that really fast. Yes, it does. These are the 3 members we have, but I'll use R, C, and O just for right now to make things a bit simpler. So we want to know from this location, how many more moves possible can we make? Well, from here, I'm going to use maybe purple. We could go over here. So that's 1 move we could make. We could go over here. So that's 2. And also we can't go here because it's outside the board, so we're not going to count that. We could go over here. This is a legal spot, so we're going to add that to that counter. And then let's see what else we have. Well, we can't go over here because we already have a number over there, which means we already used that spot for something else. Not going to add anything. We could go over here. So add this to be a 4. We could go over here. This is a vacant spot. Make that a 5. And once again, we can't go over here. This is outside the scope of the board. So for this block, the amount of onward moves would be 5. So now what you have to do is you have to do this for all the other remaining green blocks. So you want to have a vector of these position objects, store the row and column positions, and store from that location how many possible moves can you make. So you want to store those all into each individual element, and then return that vector back. So it's going to be called from some function. We want to return that back, so it can be used to help us pick our next move when we're currently on a spot with our knight. So now let's go over the finally complicated function, the recursive part, which will implement this KnightTour. All right, so the last part will be the Boolean function KnightTour. You might notice that we have actually two of them, so we're overloading this KnightTour function for this class. This function is going to be called in main, so I have a main provided for you. It's also going to be automatically linked up on code grade. So you'd only have to submit just this implementation file. So the header file is kind of given to you already. This will be the contents you're going to have to use. These are the function headings you're going to have in your implementation file, and the main will be given to you. So anyway, this function will be called in main. So in main, the user asks, or the program asks the user, of what's the initial location of the knight. And whatever number it gives the program, we're going to pass those two into this function. The row and column indices of where the initial location of the knight is going to be. In this function body, it's actually very simple. I think I have it written over here as well, just to make things really easy for all of us. This function will only have as one thing. That's the only thing you're going to have in this function, KnightTour. So you're going to make a call to the function, the other KnightTour function, pass the same row and column indices in, but then pass in 1, which is the tour index. And now we're going to go over this KnightTour function. I think it has these 6 steps right there. To sort of go, I'm going to go over this right here, and I'm going to definitely do an example to kind of help you understand what this function will actually do. So when you first enter this function, you're going to set the board at location RC with whatever is stored in this number, which initially will be 1 when you first call this function. Then check. If the board is full, return true at this moment right away. Just return true immediately if the board is full. So you have to use that fullBoard function right here. Step 3. So right now you're at location RC. So you want to go ahead and get all the available moves you can make from RC, along with the onward moves you can make. So you have to make a call to that function available moves and pass in this coordinate, these 2 coordinates right there. And now here's the only, challenging part. So for this heuristic-based approach, for this knight's problem, you want to pick the move that has the fewest number of onward moves basically. So remember, available moves function returns back at most 8 possible moves. And then from those 8, you gotta find, well, which one is the smallest one. And then you want to know what the row and column index is of that smallest move. Well, it's okay because remember that position vector, each element will be a position type, and a position type has the onward moves amount from that position along with its row and column amount. So basically, once you find the move with the smallest number of onward moves, you're going to make a recursive function call. You're going to call this function by passing in a different RNC, well, the RNC of the next available move with the smallest number of onward moves. And you're going to pass in a different value for tour index. So possibly pass in tour index plus 1. And then what happens after you made a recursive function call, this function returns a true or false. So when you make this recursive function call, if it returns true, return true immediately. It's going to relay that true all the way back. And if it returns false, then you're going to have to sort of go back to step 4 and pick a different available move and then try the same thing again. So at some point, the whole board will be full and return back the it returns true all the way back to the beginning. Now, one thing I forgot to put into this PDF, so I'll write this over here just to kind of make it clear, is you want to also increment what's the actual variable name? I think it's called functions called. Increment functions called by 1. You want to count how many recursive function calls you made, just so you have an idea of how much work it took to get the solution. So this basically was return true back all the way back to main. Then in main, we're going to go ahead and outputs the board for you. So I'm going to go ahead now and just try to give you an idea of how this function would actually, sort of how you would actually think about this function in more of a graphical approach. All right, so this is going to be one of the examples that was in the PDF. So we first have our knight start off at this location. So what happens is in main we call a function KnightTour, and within that KnightTour function we simply just call the overloaded KnightTour function. So we pass in, I guess, 3, 4 into the function, and tour next will be 1. So we're going to go ahead and just mark this location as index 1. So then what happens is we have several, so in the function body after we have this 1, so I'm just going to go ahead and just write this here for us. So we have KnightTour, we pass in 3, 4, and 1 into the function body, or into the function parameter list. So from here, as we know, then we go ahead and call the getAvailableMoves, which returns back all the possible moves you can make from this position. So as we already know, there'll be 8 moves. We can try this location, you know, that's standard knights, moves in the chessboard. It's going to be all the moves that I can possibly make. And each of these is actually all valid. So then that function returns back these 8 moves. It returns back each of these moves' coordinates and the amount of moves it could make from that location. So from the output I can see here in the PDF, it appears as if this location, this one has the fewest number of onward moves. So then this one would get chosen next. So what happened is we go ahead and say, okay, well, this location, obviously, it's going to store the indices. Row is 2, column as 6, onward moves is, well, whatever it is. I don't know what is off the top of my head, but it's the minimal of all these 8. So then what happens is we're going to go ahead and call, so in this function body, it calls KnightTour to 6, and we're going to pass in 2 this time. So notice over here, it was 1, now it's going to be 2 for that tour. So every time we call a function, we add 1 to our tour index and pass that new amount in, like this. So, oops. So now what happens is we're going to currently be at this location, right here. So we write the 2 into this position, and then from here, we try to find all 8 of its moves it can make. So of course from here, we can go to this location, this location, this location, and this and this. So obviously, this one has the fewest number of onward moves because, well, we call the function getAvailableMoves. It returns back these 5 possible moves. And that one has the smallest number of onward moves. Remember, each element in that vector is going to be, what's it called? It's going to be a position object. And remember, it stores the row, column, and the onward moves from that position. So then it's going to recursively call, it's going to choose that location. So it's going to call KnightTour. This is actually how, so remember from CS302, you have a system stack that maintains all the function calls. So now we're going to go ahead and pass in 0, 7, and 3 gets passed. So we're going to do this whole process. And at some point, what's going to happen is sooner or later, we're going to go through all these blocks. So we're going to keep on calling more and more functions get called along the way. And at some point, we're going to have a KnightTour will be called. To have some some row, some column, and the tour will be 64. And then what's going to happen is it returns the value true, because it's actually now everything has been filled. So then it returns back to the previous function call. And what happens is in previous function call, it awaits sort of the function that it spawned. It returns true, so true is returned also by that function. So let's go back to the very beginning part of this. So let's say over here. So KnightTour 073 returns true as well. So the way this works is when we were sort of sitting on the function KnightTour where we had 2, 6, and 2 passed in, that function made a call to KnightTour 073. And that function call returned back true to us. So since KnightTour 073 returned true, then KnightTour 262 also returns true. And then we get back all the way back to that function where we have KnightTour 3, 4 only. That returns true back to main, and then main will go ahead and output the entire board. Now, I don't think with this heuristic approach this will happen, but in theory you have to write this code, just to be careful, you have to write the code either way. So let's say, just in an alternate universe, for example, what if we have the following scenario happens? Let's say we have KnightTour 32 happens, let's say. And we chose spots in a certain way that from this location, let's just say we didn't always pick the best move. So what happens is, let's say we're at 32 for index, and we have no move we can possibly make. So from this RNC we're passing in, there's no possible moves, then a false is returned. So what happens is, when a false is returned, you return back to the previous functions. Let me just go ahead just for now, let me try following. Let's say for example KnightTour 073. Let's say this returns false, because for some reason when we were at this position we couldn't advance the game any further. Then what happens is we go back to the previous function call 262, and we sort of remember our remaining moves. We had these moves that we had left. We had these moves like this. We chose 3, we chose this one, but this one actually wasn't the best one. So it turns a false, we have to pick a different location this time, and then respawn new function call. We pass in 3 into that tour index, but on a different row and column index. Now I think with our heuristic approach, a false should never get returned. It should just automatically go through 64 function calls. But I'm using a heuristic approach because potentially it can take a very long time if we don't use this heuristic approach. It could take, it could take into the billions of function calls, and then I guess it would time out on code grade when running the actual programs. A heuristic approach would make it go faster, but still write the program where if let's say you recursively call another KnightTour function and returns false, you want to just sort of try to at least think about how you would handle the case where what if we're at a certain position and from that spot there's no moves the knight can possibly make. Well, in that case it returns a false back to the previous function, and from there the previous function has to pick a different location this time to try to advance the game. Hopefully that does in fact make sense. So anyway, that's sort of the recursive function for this program. So let's go ahead and sort of show the main portion. I think I have my videos right there. So anyway, maybe I'll pause this then. So anyway, here is the main given to you. So pretty much all we're doing is we're going to create a pointer of type knight type. We ask the user for dimension. Then we allocate allocate an object to this pointer. We ask user for initial knight position. Then we go ahead and just call the function KnightTour. If it's true, we output knight for the win, output tour. Otherwise, we just don't do anything. but this function would just call the KnightTour, and this function KnightTour internally calls the overloaded KnightTour function when it has 3 parameters. But anyway, when true is returned back, it outputs for the win, and then outputs the tour, which outputs the board along with the amount of function calls made. And of course, it deallocates the object, sets it to null, and asks the user if you want to go again. If they do, it'll just keep this game going over and over again. So this will be given to you. So for submitting to the, when you want to submit this program, you have to only submit the knighttype.cpp. The header file, you don't have to upload that, because I'll have that header file and this main up on CodeGrade already. So we'll simply just link your knighttype.cpp, the implementation file, to the main on CodeGrade and that header file on CodeGrade. And it will go ahead and sort of do, actually, yeah, so actually I may not have a header file up there, because if in case you add extra private functions to your class, then the header file won't link with that. So I guess you have to upload your header file and your implementation file. My mistake on that. But the main, you will not have to modify the main at all. Just upload the header file and the knighttype.cpp implementation file, and it will link that to the main on CodeGrade, and it will just go ahead and just run this program. So I hope the video did sort of give you an idea about this. So I guess happy coding, and till next time.